And this is collaborative work with Oregon State University, and where I'm presenting our work on using deep reinforcement learning for the CASI robot. And so I will briefly talk about reinforcement learning so that we are on the same page. In reinforcement learning, we are trying to learn a policy that we call pi, which is parameterized by a theta, which in our case is a neural network. And the policy takes the input as the robot state, or if you have any measurement of the environment, you can also take the environment state as your input. And the output of the policy is an action that the robot can take. So the robot, after the action is taken, the robot will evolve to another state, and the environment will also give the policy a reward. So the goal of reinforcement learning is to maximize the sum of the rewards over some time window. And so, reinforcement learning has been very successful in training policies for locomotion in the past few years, at least in simulation. And you can see they can generate really natural-looking gaits. However, there's a caveat. You need to tune your things really, really carefully to make things work. Otherwise, you get this crazy motion that, well, nobody will try to put on the robots. And anyway, so our question is, can we learn reliable policy for this robot CASI? Well, not exactly. So we tried this by just reward CASI to walk forward, and it generates some really crazy gates that obviously no one will put on the robot. And so the way to tackle this is usually reward tweaking. So as a designer, you have the authority to design a reward to make your robot walk, and then you run your reinforcement learning algorithms, and then the algorithm output a policy, and then you try it on the robot, and you see what you don't like, and then or what you want the robot to do more, and then you just add another term to your reward function, and then run your fighting your policy again, and get another policy, and then you just go on until you are satisfied with your result. And so this is really tiring and require a lot of manual tuning. And instead, we are proposing an iterative design process with several building blocks. So the first building block is just the standard reinforcement learning thing. And then we also have a supervised learning used for policy cloning. Suppose you already have a policy pi2 and you just want to copy what it does, then you can just collect state action sample from your policy and get another policy that just did what it does. So you might wonder, why do we need this since we already have pi2? Well, you might have many different policies for different things. For example, you might have the robot to walk forward, and you might have the robot to walk backward, and you can just learn them separately and then distill them into one single policy that can do it all. And then finally, we have another building blocks called constraint RL, in which case you are trying to imitate an expert policy pi1, and then you also want it to be optimized for another reward R2, and then in the process, you get a new policy pi2 that is optimized for your new rewards and while stay close to your original policy. And then you can put these things together and iteratively design your policy. So I'll give you a quick example. And so we just saw that just ask the robot to walk doesn't work really well. So instead, we are checking a reference motion to make the life of reinforcement learning algorithm easier. So here is our reference motion for a stepping in place gate. And we put it to our RL algorithms, and it output a really nice stepping in place gate. Well, you might think it's nice, but if you zoom in, you can see the pelvis is really shaky. And we put it on the robot, it's shaky as well. So while in simulation, we don't really care, on the real robot, it's really harmful. And so the naive approach will be to design another reward that penalize pelvis angular velocity. However, we try it in simulation, it forgets how to step, and it doesn't really do a good job at this stable pelvis. And then, so instead, at iteration 2, we are using the constraint RL building block that I just showed you. So we are trying to imitate the shaky stepping in place gates while also optimize for less angular velocity for the pelvis, and we get a really nice looking stepping in place gates on the real robot. And then we not only want the robot to just step in place, so we also train it to walk forward and walk backwards separately, and then just combine them together into one policy. They can do it all. And it works on the real robot. And then, yeah, so it works with a variety of reference motion. In this case, we are using IK tools to generate a stepping in place gate. And for walking forward gates, we just naively translate the robot forward. And it still works, so we go through the same process that I just mentioned. And voila, another policy that works on the robot. And so we design multiple policies using this process. And just to highlight one of them, so we go through the checking a reference motion and then optimize for stable pelvis. And then in addition, we ask the robot to lift the feet higher. And here is the result that we get. And just for the fun of it, we put a board in front of it. And so you can see it's quite robust. Yeah. Eventually it falls, but I just stopped the video there so you can see. Yeah. And so I want to talk about a little bit about sim to real as well for the remaining time. So for doing reinforcement learning, we can only do it in simulation because running IL algorithms on a real robot is really harmful to the robot. It will fall like thousands of times until you can learn a reasonable policy. So we can only do it in simulation. For that to happen, we need an accurate model which require very good system ID, and then we also model the delay in the system in our simulation. And then we are also, so in simulation, we have the access to the true state of the robot, while on the real robot, we can only estimate the state using some noisy sensor data. So we incorporate that in our simulation as well. And then we find that using time-based control is really important. So as an input to our policy, it also has access to the time. And so we find that it's more robust compared to only state-based control. And then I want to highlight that we don't need any dynamic randomization. So dynamic randomization means that in simulation, you will perturb your dynamic property of the robot to some degree, and then so that the policy can work in a variety of different models that can account for the discrepancy between simulation and the real thing. So in this previous paper by Google, which they try to use do sim to real on a small quadruped, they perturb their mass like by 20% and inertia by 50%, even though they also do those accurate modeling things that I mentioned. Well, in our case, which I think our robot is much more difficult to control, we don't really need to do that, so that's kind of a surprising result for us. And with that, I want to thank our collaborators at Oregon State, which thank you for trying out our crazy policy on your robots. With that, I'm happy to take questions while you guys enjoy this pushing test.
I guess when you say time-based policy, you mean the time gets reset presumably by triggers?
Yes, so the time is reset every walking cycle.
And then would that be roughly equivalent to maybe make a phase, to put it, just tell the neural net to put a phase variable in instead of just explicitly demand of paying attention to phase, or does it really have to be open time-based?
What do you mean by phase, sorry?
Well, so you put in state estimation, you could have just a state-based control.
Yes.
And you say that doesn't work as well as putting in time, but you reset the time every step. So it seems like really in the background you're just looking for a phase-based control. And if you just put an explicit phase estimator, would that be good enough to replace your time-based control?
I haven't tried that. We haven't tried that yet. I think that should work. Yeah. Thank you.
Any more questions? Go ahead.
Can you say anything about using a hierarchy of policies and how this might fit into this iterative learning?
Hierarchy? Yeah, so currently we still need so the robot can work at a variety of speeds, which is commanded by the operators. And so you might have another policy that tell the robot what speed you want to do, and you can also feed it with your environment information with like obstacles, and then the robot can learn how to steer itself across the obstacles using different speeds, etc., etc. Is that a question? Yeah.
Ask more later.
Yeah.
Any more questions? Okay, let's thank our speaker.